Hi, everybody. Let's talk today about dot product and cross product. When we compare the dot product and the cross product, there are three main differences between them. Number one is the dot product returns a number, also called a scalar, and the cross product returns a vector. Number two, the dot product works in any number of dimensions, and the cross product only works in 3D. And the reason is because in 2D, for the cross product, there is a limited time when you have a vector perpendicular to a given pair of vectors. And in 4D or more dimensions, there are an infinite number of vectors perpendicular to a given pair of vectors. So that's why we only use cross product in 3D. And number three, the dot product measures how much two vectors point in the same direction. And I have explained that in more detail in my dot product video. And the cross product measures how much two vectors point in different directions. Again, I want to bring up what you are giving in the FE handbook, and also you have available during the exam on vectors. And here you have, as we've discussed, the dot product formula, A dot B. And you're actually told here the dot product is a scalar product. So it returns a scalar, a number. And this is important because I've seen questions, and maybe you have seen it too, where the question on the exam can be as simple as, what is the result of a dot product? Also, you have the formula for the cross product, and you are told here the cross product is a vector product, meaning you are getting a vector when you do the cross product. Now, moving forward, let's talk in parallel about dot product and cross product. So, number one, we know that the result of a dot product is a scalar or a number. And the result of a cross product is a vector. And we already discussed this, but I will go ahead and quickly take two vectors. Vector A going to be equal to I plus 2j plus 3k. And if I take vector B equals to 2I minus 2j plus k. And if I was to do A dot B, I'm going to get 2. So 1 times 2 is 2. 2 times minus 2, get minus 4. 3 times 1, I get plus 3. So the result is going to be 2 minus 4. It's minus 2. 3 minus 2 is 1. So as I said before, the result of a dot product is a number. And now if I'm going to go here on this side, then I'll do A cross B. And if you remember from my videos, the way to do this, or the easiest way, I think it is to just do the matrix determinant. So you do A, J, K on the first row, and then the second row, you put the coefficients of the vector A. In my case, I'll have 1, 2, 3. And for vector B, I'll have 2, minus 2, and 1. And now let's just calculate the determinant. I have 2I plus 6j minus 2k. And then the other side have minus 4k plus, we have 3 times minus 2. So we get minus, and minus from the formula, it's going to be plus 6i and minus j equals, and let's reorganize here. We have 2i plus 6i. So adding the I coefficients, I'll get 8i. And then the j, have 6j minus j, have plus 5j. And the k, I'll get minus 6k. So here it is. The result of a cross product is a vector. Now, 2, the dot product works in any dimension, and the cross product only works in 3D. So the dot product is having 2 vectors, angle theta between them. And we can draw this in any dimension. So A dot B can be in Rn, any dimension. When we have 2 vectors, to A and here B, let me just go back here and do A and B as well. So when we have 2 vectors in the cross product of 2 vectors, I should say, we know that the result of a cross product is a vector that is perpendicular to both A and B. So the result is vector C perpendicular to both A and B. And in 2D, if we were to draw this in 2D, imagine how in 2D, the only case I can think of when you would be able to draw this is when A and B are collinear. Let's say this is vector A and then another vector B. And this is the only case when you're going to get vector C perpendicular to both A and B. If you have vector A, say this way, and then vector B this way, there's really no way we can represent vector C perpendicular to both A and B in 2D. And in 4D and more dimensions, as I said, there are an infinite number of vectors perpendicular to a pair of 2 vectors. So that's why cross product is limited to 3D dimension, to R3. And number 3, we've said that the dot product is a measure of how much 2 vectors point in the same direction. So if I'm to write A dot B, we have 2 formulas. We're going to write AX BX plus AY BY plus AZ BZ, where this also equals to magnitude of vector A times the magnitude of vector B times, I will not, cosine theta of angle between them. And cross product is equal to magnitude of vector A times magnitude of vector B times sine of angle theta. Also, as you know, cross product can be, as we've shown, it can be calculated by calculating the determinant of the 3x3 matrix. Okay, and then you put the coefficient AX, AY, AZ, BX, BY, BZ. So let me take this vector A and vector B. Let's draw a perpendicular to vector A, to vector B, from vector A to B. And if this is the angle theta between them, let's see this distance over here. I will call it, AX, because it's, let's say it's in the X direction. So it's AX. So let's see if we apply cosine theta in this right triangle here. Cosine of theta, we know it is the adjacent over hypotenusa, which is magnitude of vector A. So from here, the AX is equal to magnitude of vector A times cosine of theta. So now let's go back to this formula here, and I will rewrite it here. A dot B equals, I have magnitude of vector A cosine theta is equal to AX. So I'll write AX times magnitude of vector B. So if you look at this here, what a dot product is the vector B times the projection of vector A onto vector B, which is explained. It's, imagine if you have a lantern on top of the vector A, is that projection of vector A on vector B. In other words, this can also be explained as how much of vector A goes in the same direction as vector B. So again, the dot product is the vector B multiplied by how much of vector A goes in the same direction as vector B. If we go to the cross product, we've learned that the cross product is the exact opposite. So let's see how is that. If I'm gonna draw the same vectors, A and B, this is the angle theta. And let's say I'm going to draw a perpendicular line to vector B. And let's put this distance here as AY. If I was to do sine theta within this right triangle, I'll get the opposite, which is AY over magnitude of vector A. And from here, AY is equal to magnitude of vector A times sine theta. And again, if I'm coming back to this formula here, and I'll rewrite it down, A cross B is equal to A sine theta is AY, so I'll do AY times magnitude of vector B. So what this means, we have magnitude of vector B, and then how much of vector A points in a different direction, I mean. Do you see the difference between the dot and the cross product? Is the actual opposite. So the dot product is equal to vector B, and then how much of A goes in the same direction as B. But the cross product is equal to vector B times how much of A goes in the opposite direction. And that's why in the field of mechanics, as you know, the most common application for the cross product is the calculation of the moment of a force about a point, which is given by M equals to R cross F, where R is the vector distance from the point O to any point on the line of action of the force. Okay, guys, I hope this brings up a little bit of light in the dot product and cross product. Now let's work on a few examples. What is the angle between lines AB and CD shown in the figure? So we're given two lines, we have the coordinates of the lines, and we have to calculate the angle between them. Every time you're given to calculate an angle between two lines, between two vectors, I want you to think right away about a dot product, because we have two formulas for the dot product, and especially if you have the coordinates and the vectors, you are able to calculate the angle between them. So let's figure out which angle we have to calculate. So first, let's think about this line AB. If we were to calculate the vector AB, we're going to have the coordinates, which is let me see, we have bx minus ax, and then we'll have by minus ay, and we'll have bz minus az. And this is going to give us bx, we have 4, let me write it down, 4 minus 3 plus 3, 2 minus 5, 3 minus 2, and this will give us vector AB. Let me write it down again. AB is going to be 7 minus 3 and 1. Same thing, let's do vector CD. We're going to have dx minus cx, dy minus cy, and dz minus cz. And this will give us 3 minus 3 plus 3, 6 minus 1, and minus 2 minus 4. And vector CD is going to be 6, 5, minus 6. And now vector. If we were to imagine this, if we were to translate CD all the way to this point, we're going to have and draw a parallel line to CD. This is vector CD, and this is vector AB, and this is the angle theta between them. So let's write the formulas and do first A, B dot C, D. So we're going to have 7 times 6, we're going to get 42, minus 3 times 5, minus 15, 1 times minus 6, minus 6. And we are going to get 42, 15, minus 6, minus, getting 21. And now I'm going to use the other formula of the dot product, which tells me that AB dot CD equals to magnitude of AB times magnitude of CD times cosine of the angle between them. So now I will go ahead and take my time here, calculate the magnitude of AB. I'll just do it here. Magnitude of AB is equal to square root of 7 squared plus minus 3 squared plus 1 squared. And this is going to give me square root of 59. And now CD, I'll do magnitude of vector CD is equal to square root of 6 squared plus 5 squared plus minus 6 squared. And this is going to give me square root of 97. So now that we have the magnitudes, we can go ahead from these two equations, calculate for cosine of theta. So cosine of theta is going to be equal to, from this formula, I'm going to get AB, vector AB dot CD dividing by magnitude of AB multiplied by the magnitude of CD. And we know dot product we have calculated here is 21 divided by square root of 59 multiplied by square root of 97. And this, use your calculator to calculate that. So I get 0.278, I'll round it up. It results that theta is going to equal to arc cosine of 0.278. And if you use your calculator, you should get that theta equals to 73.88 degrees, which if we round it up, we're going to get 74 degrees. And looking at the answers, the correct answer is B. Now, problem number 2, what is the area of the triangle ABC shown below? A quick reminder here on my previous video, we have discussed what is the cross product representing. And I will go again back to the FE handbook, try to remind you that if we look at the FE handbook, the area of the parallelogram is actually the formula for the cross product. So the magnitude of the cross product is actually giving you the area of the parallelogram. When you are asked to calculate the area of a triangle or of any other shape, as you see here, and you're giving the coordinates, you have to think about cross product right away. So let's say we're going to have vector AC and vector AB. Let's do vector AB and calculate the coordinates again. We're going to have, I'm just going to do it right away. We'll have 4 minus 0, and I have 4. 0 minus 5 minus 5. 0 minus 0, 0. And we'll have AC, vector AC, going to be equal to 0 minus 5 and 4. And now we'll do AB cross AC. And this is going to look like this. We're going to build our matrix with the I, J, K, first row. Second row comes AB, 4 minus 5, 0. AC, 0 minus 5, 4. And let's calculate the determinant. Gonna have minus 20I plus 0 minus 20K minus 0 minus 0, and we have minus 16J equals, so let's see, what do we get? We get minus 20I minus 16J and minus 20K. So this is the resulting vector. And now I told you that the cross product, or the result of the magnitude of the cross product, is actually giving you the area of the parallelogram. But now we have a triangle here, we don't have a parallelogram. But if you can envision here, if I was to draw a parallel line to CB and then another one parallel to AB, this is the area, the magnitude of AB cross AC gives you the area of this parallelogram, right? And what we need is just half of that area. So the area of the triangle ABC that we are asked in the problem is going to be equal to half of the magnitude of the cross product of vector AB and AC. And this is going to be equal to half 1/2 multiplied by, and the magnitude is going to be minus 20 squared, or square root of minus 20 squared, plus minus 16 squared, plus minus 20 squared. And this is going to be equal 1/2. I'm going to use my calculator. I'm going to have 20 squared, 400, 16 squared plus 20 squared plus, and I get square root of 1056, and I get 16.25. 24/8, I'm going to round it up to 25. So the area of this triangle ABC is 1625 units squared. And looking at the answer, the correct answer is C. So pretty easy problem if you know that the magnitude of a cross product is the area of the parallelogram. And if you have a triangle, you need to divide that by 2. Thanks for watching, guys. See you next time.